Hey guys, this is Terence. Welcome to the new episode of RhinoPython and GhPython Playground. And our today's topic is this canopy. It is a fancy looking canopy, but the mechanism behind this pattern is much more straightforward than it's looking. It is just overlaying a hexagonal pattern on the untrimmed surface. I'm pretty sticky about the untrimmed surface because that's the basis of all our works. And I prefer to separate today's structure into two videos. This video only talks about how to construct and tweak the frames or the skeletons of this structure. And in the next video, I will talk about how to create the filling part. I mean, the white part in this image. So let's take off. Okay, now let's use the sketchbook to explain the logic behind the structure. And it is our custom. And first, let me draw some hexagons. Here, I prefer to connect these hexagons in a way of a honeycomb. The honeycomb is a structurally reasonable pattern with a very high efficiency in the space and material usage, so I think that will be ideal for the construction process to save the material and also to make the whole structure very strong. Okay, I think we have enough hexagons. And the next thing is we will overlay a regular point matrix on this honeycomb pattern. Then we will find the tricks behind this pattern. Okay, let's keep doing this. Add one more row of the points. I think 3 rows of points are sufficient for us to analyze this pattern. So I will just stop at here. Now, the next thing is to label all the points. Let's start from the columns. Sorry, 2. Here's 2, 3, 4, 5, 6, 7, and 8. Now let's go to the rows 0, 1, and 2. Okay, we can think about how to filter and modify this point. Make these points the corner point of the hexagons. Then we can just connect all the modified points to create a hexagon. And I think I can draw a one more row of points that will be more straightforward. Where is it? Oh, it is here. 3. We can see all the odd rows sharing the same logic of modifying and filtering the points, and all the even rows sharing another logic. So we can just start from these even rows. Let's take a look at each of these points. Maybe we can just move each of these middle points on one edge of the hexagon pattern, move them some distance to the left and some distance to the right. How could we get to know the distance? Let me draw a small triangle here. This is a triangle, and the angle here will be 30 degrees because this is a hexagon pattern. So according to the trigonometry, this distance equals to half of the edge length. So we can say the moving distance could be this distance could equals to the edge length E and G length divided by 2. So we can know, okay, in the odd rows we do the same logic in each of these points. But how could we define which point we should move? Let's take a look at this index 1, 4, and 7. What kind of logic they are sharing? What I find is if this index modulo by 3 equals 1, that will be the center point of each of these hexagon edges. So I think this is gonna be an important rule here. And also we can use the same conditional here. We can use the same condition here to filter the points on the odd rows, because you can see here, in the even rows, we move the point in this index left and right, but in the odd rows, we can just skip the point on this index. So we can say the rules is going to be, on the even rows, if the index modulo by 3 equals to 1, then we move the point left and right with the distance, which is the half of the edge length. While on the odd rows, if this condition is also true, we can skip the point. Then we will have all the points we need locate at the corner of each hexagon. What we need is just to connect all the newly generated points. Then we can have this pattern. Okay, I think we can try to achieve this in Rhino and in our code editor. Okay, now we can set up our basic working environment here. We can add a Python script node and right-click it, show code input, and input is path. Then create another node, which is the file path. Right-click, synchronize it, and select one existing file, which is our Python code. Connect it to our Python node. Finally, add a panel to show all the printed stuffs. Now we can check if these two files are successfully connected. I can say print, go, save it, and the Go shows up here. We just finished our connection works. And before start writing code, I want to add some more inputs here. The first one is the surface. The second one is gonna to be U number, which means the U division, the division along the U domain. And also the V number, the divisions along the V domain, along the surface's V domain. I will create another node called surface, which is a surface container. Right-click, we can convert this surface into our Grasshopper workspace. Now I just want to hide this surface here. Connect it, right-click, and set type hint to surface. We will provide 2 integers to both of the inputs. I can say 8 and 8 for another one as well. Align them a little bit. Oh, it looks not good. And the first thing I want to do in our code editor is to ensure these 2 inputs are integers. So I'd like to write U number equals to integer U number, and V number equals to integer V number. Then we can start creating functions help us to divide the surface. The first function I want to define here is the divide domain, which takes 3 parameters: the surface, the U number, and the V number. Inside here, I want to first declare an empty point dictionary, which used to contain all our going to be generated point. And I want to get the surface's U domain first. Use the function rs.surface domain with an input surface and the direction 0. 0 indicates the U domain and 1 indicates the V domain. We will do this very soon. V domain equals to rs.surface domain with the input surface and the direction of 1. Now we have the domain. We want to have the steps, each step of the domain according to our divisions. As we define the u domain, u number and the v number here, we want to use this number to divide the domain into the equal distance. We can say u step equals to u domains end value minus end value is 1 minus u domains start value, then divided by the u number, then we get the u step. We do the same thing on the v step. We can say v domains end minus v domains start divided by v number. The next step is we need to first loop over this u number. We can say for loop over this v number for v in range v number plus 1. And here we want to first find the v parameter, which equals to v domain 0 plus v multiplied by v step. And we get our v parameter here. We want to next set the u index or initialize the index u index as 0. Then we can loop over all the we can loop over u numbers. We can loop over u numbers. It's quite convoluted. U number plus 1. It's a nested loop for us to loop both directions. Then in each step we create or we filter or we modify points according to the rules we just generated. According rules we just discussed it. I want to open up the sketchbook. Open the sketch we just created as a reference here. We need to first check if now we are locating at the even rows or the odd rows, and we also need to check this if the index modulo by 3 is it this expression equals to 1. We need to check both conditions. So we should say if u modulo by 3 is equals to 1 and v modulo by 2 equals to 0. This line of conditional statement means if it is locating on the even rows and the point index is 1, 4, 7 or something following these rules, we executing these following codes. We want to first extract the u parameter at the specific position. U domain plus u minus 0.5 multiplied by u step stp step. Yeah, and we can put this point into our point dictionary. Here means we want to first move this point left half edge distance. So we can say points with the key value v and u index equals to rs dot evaluate surface with 3 inputs. The first one is the surface and u parameter we just created and the v parameter. Then after this we need to add u index with 1, add plus 1. Now we have this one, we need also to move this point to the half distance right. So we should say we should update this u parameter. We copy this and paste it here. Modify this minus to plus. Then we do the same thing here. Oh, sorry. Can paste the identical codes here. And I think we just finished these rules, this moving left and moving to the left and moving to the right rules. Then we will write another conditional statement, else if u modulo by 3 not equals to 1 and v modulo by 2 equals to 1. This means this conditional statement means when our then we are locating at the odd rows, and the point index modulo by 3 is not 1. That means when on this point, on 0 to 3 and 5, 6, in this kind of points, we can executing the following codes, or we just skip those points, those unnecessary points, and we can say u parameter equals to u domain 0 plus u multiplied by u step, and we add point. We copy this line of code and paste it here. Then we need to also add u index by 1 plus equals to 1. After we finish this nested loop, we need to return the point dictionary. And for now, no errors pop up here. That means our code is functionally written. And I want to call the code, call this function here. I want to say a equals to divide domain with the surface u number and v number. And now there's no point pops up in this workspace, because the point structure is a dictionary. The Python node, sorry, the Grasshopper cannot recognize dictionary, so we need to convert the point dictionary to the point list here. So we just need to say a equals to a dot values to convert the dictionary to the list. Save it, and I think we have some indentation error here. Just indent back and save it. Now we have all these points. It's quite apparent that we don't have enough v domains, v numbers. So I want to create a larger slider for the v number. And now we have our point distributions here. We can just use this point to create the hexagonal pattern. But before that, I want to write some code for debugging. I want to write some code to show the point index or point keys on each of the points. I want to add another output called b. And what I want to do is to loop over all the indexes, loop over all the keys in this point dictionary. So I can say b equals to a dot keys. That might works, and a equals to a dot values. Save it, and let me check. Yeah, we have all these key values. Now let me try to place the key values to each of the points. what I want to use is the text tag 3D, and we have our locations here and text point here, and yes, now you can see we have these indexes, but the size is not preferable at all. So I want to adjust the size to make it smaller. Maybe 0.5 could be a desirable one. Or 5.6, 0.6 maybe. And I think, and with this index, I think we can just go ahead to find a way to connect these points according to each of the points key values. To do this, we need to declare another function which is called draw hexagon, and with only one input, which is the point dictionary. Inside here, I want to first declare an empty list to contain all our polylines, and then I want to calculate the max v index and max u index. Use the function max. Inside this function, I want to use the list comprehension to loop over all the v index in the keys of the point dictionary. Key in pt dictionary. And then I want to do this on u domain, also max function. Keys, key with the index 1 for key in point dictionary. Then I can print these two values to check are they correct. I want to do it here, do it down here. Call the draw hex with input a, because a is a point dictionary, but I should do it here. Save it, and yeah, we have this Vmax value which equals to 20, but Umax value just equals to 6 because we filtered or we modified point. These two values are not necessarily equal. Then we have these two max values. We can first loop over all the V values in range Vmax -1. Then we loop over all U values in range Umax. I think we should add some codes to make it more complicated. Maybe we can start from v modulo by 2. Sorry, let me re-explain this. We want to draw the hexagonal pattern in this way. We can do the 0, 0, 1, 1, 1, and 2, 1, 2, 0, and 1, 0. Use these 6 points to generate hexagons. This is the rule in the even rows, but to the odd rows, the first point is not start from 0. The first point is start from 1 because the hexagon in this line looks like this. So we can't say we loop over all the U value. We just need to start from V modulo by 2 to the Umax minus V and modulo by 2 with a step of 2, because we want to skip these middle points. We do 0, 0, 0, then the next hexagon locates in 0, 2. So there will be a gap between them we need to skip. Okay, let's keep going on. Now is the hard coding part. We need to extract each of the point. We can say the first point is the PT dictionary with a key value v and u. Let's copy and paste this line 6 times. The second point is gonna be vu plus 1 here. The third point is gonna be v plus 1 and u plus 1 is this point. And the fourth point is going to be v plus 2, u plus 1. The fifth point is v plus 2 and u. The fifth point is here now, v plus 2 and u. Then the last point is gonna be v plus 1 and u. Then we just need to put all these points into a point list. Let me hand put this one, PT1, PT2, PT3, PT4, PT5, and PT6, and ends up with PT1 because we need to close the shape. Then we can generate a polyline with the function rs.add polyline with the points pts. Add polyline here. This should be a lowercase. Then return. After finishing this nested loop, we return the polylines. Save it. No errors, and we want to put these polylines to a new output, which is C. I just add a C equals to the draw hexagonal here, and you can see we have this Let me create new curve container here and hide all other information. Then it will be very clear. And as you can see, there's some extra point here that cannot meet our 6-point rules of creating the hexagonal pattern. So I will add another debugging codes, add some other debugging codes here to avoid or to escape these extra points. And this is gonna be if u number is smaller than 5, the u number equals to 5. And if u number is larger than 5 and u number minus 5 modulo by 3 is not equals to 0, we should do u number plus equals to 3 minus u number minus 5 modulo by 3. This looks quite complicated because I did a lot of tests. Then I find this line of computation will help us to address the problem. I don't know how to explain that here, but if you are interested, you can try to explore the logic behind it, or you can just apply these codes to avoid many weird points or many weird patterns, I think. Let me save it. And yeah, you can see we just get rid of the extra points and make all the points connect to at least one of the hexagon on this pattern. Now we can just modify these numbers to create to create a desirable patterns. For now, this layout looks pretty ordinary. The next thing we want to do, and also the final thing we want to do today, is to add some dynamic features to this pattern. We will use the knowledge of attractions, or we will use attractors to modify this pattern according to each point's distance to that attractor. So here we need to define another function which is called offset points that will take 4 parameters. The first one is the point dictionary, then an attraction point, the magnitude, which indicates the distance we want to, the max distance we want the point to move, magnitude, and also the surface with a column here. And inside here, we want to first calculate the max distance between our test point and the attractor. But first, I want to pass this function and add attractor and magnitude to the input. I want to add 2 more inputs here and move these nodes away from the Python node. This one is gonna be a TTR. PT is attractor point, and the second new input is the magnitude. And here I want to add 1 more node, which is a point. Right click, set 1 point. I can place it anywhere, somewhere in this workspace, and connect the point to the input. The magnitude, I will set it to the 1.5 for now. And we have these 2 inputs. We can keep working on this function. We can say first we want to calculate the max distance between each of the points to the attractor. This max distance equals to the max value of another list comprehension, which is rs.distance. With 2 inputs. The first one is the attractor. The second one is the point, and then for point in pt dict dot values. And we copy this line of code, paste here, because the next step is to find the minimum distance. We just need to change the max to minimum and change this max function to the minimum function, and the rest part of the code will be kept unchanged. And after that, we can start to think about how to move this point. Let me make this surface visible, and we can say we want this point move along the surface. We don't want it move too far away from surface, because that will deconstruct the pattern. So to do this, we need to first find the normal value, the normal vector on this point, and use the normal vector to construct a plane, then only allow the point moving along that plane. So let's do it in our code. We can first loop over all the points. In the point dictionary, ptdict.values, and then first calculate the normal value. We can say normal equals to rs.brep closest point with the surface and point. I think we can check what this function returns. It actually returns several values. 0 is the point, 1 is the UV domain, 2 is the type, and 3, or the third, is the normal to the brep surface. So we need the third value of this the third value this function generated. We keep doing this. We can say surface pt and 3 here. Then we will use this value, this normal vector to find a plane. We can say rs.plane from normal, with a point and the normal. Then we will generate a random vector. That's a completely random vector. We don't need to care about the plane here. We just generate a vector. But before doing this, we need to import another library, which is a random library. We can say from random import some functions like random, and maybe we need a seed because we want to have control on the randomness. And here we can just set the seed as 100. Then here we can start creating the random vector. We can say rand vector ctvc is okay, equals to the random value minus 0.5. This part of code will help us generate a random value ranges from negative 0.5 to positive 0.5. And we copy this, paste again. We have these 3 random values, which is x, a random x, random y, and random z value. Then we want to add the point with this random vector. We can say new location or new point equals to rs.pointAdd. First input is gonna be the point, and the second one is our random vector. We just want this point move along this vector. We want to move it. We want to move the point to a very random direction. For now, it's not necessarily moving along the plane. The next step is to find the new point's projection point on the newly generated plane. So we can say new location, still the same value, equals to rs.plane closest point, which is a projection point. That is gonna be the first one, plane. The second one is new location. Now we have the projection point on our plane. With this, we can find a moving vector. We can say move vector equals to rs.vector subtract. Use the new location to subtract the point location. We will get a moving vector. New location and point. Then we will unitize this vector, or we can say we want to normalize this vector. We use the function rs.vector unitize, which is convert the length of the vector to 1. Then we can find the distance between the attraction point and our point. We can say distance equals to rs.distance attr point and point. Now we have the distance between our point to the target point. The next thing we want to do is to map this distance to this to the range from 0 to, let me explain this again. Then we need to map the distance of the point to the attraction point to the domain. The domain ranges from 0 to our magnitude. It's kind of remapping. So we want to say remap distance equals to an int integer sorry, we want to do is we want to use the distance subtract. We want the distance minus the minimum distance, and use this value to divide the maximum distance minus minimum distance. And because this value, this is gonna be a float value with many digits after the point. So we want to round it up. We want to have only 3 digits after the 0 or after the point. So we can say, we can first multiply this value by 1000 and convert it to an integer value, then divide it by 1000. Then we will round up this value to our target value. And at last, we just need to start moving the point according to the distance and our moving vector. We can say rs dot move object with a point, and with the vector, we will use the vector scale to enlarge our unitized move vector. And the second input is gonna be our remap distance. Then multiply by the magnitude and save the code. We can call the code just right under here before creating these hexagons. We can say offset which function? Yes, offset points. Copy this function here, paste it here. We will replace the point dictionary with a, and we have our attraction point. We have our magnitude here, and we have surface. We just need to save it, and an arrow pops up. Unable to convert the NURB surface to brep. Okay, I know where is the problem. It's here. I defined the type to surface, so it is surface. It's no longer a brep. But surface could also be a brep. If we define it as surface here, we limit the type. We limited its type. So maybe we should click here. We should make this type as a GhDoc object that will enable the surface to be also a brep. Sorry. And I think we have this pattern. We have some deformed part here, but we also have some very ordinary hexagon here. We will have a transformation from the regular one to a dynamic one. We can adjust the magnitude here to some extent that between the acceptable and unacceptable. Then we can just hide these things, hide this tag, and only leaves these polylines. We can modify these values. We can also tweak this value to get our desired pattern. And also I think we can move the position of this attraction point, and the pattern will change as well. And that's, I think that's all we want for today's video. And last but not least, this pattern is not as complicated as some of our previous works, but I feel it is very hard to explain some ideas like vectors, why I should add vector here, or why I should subtract vector there. And I feel I also failed to explain some convoluted ideas. Because of my limited English proficiency, I will improve this in the future. That takes time. So I highly recommend you guys, if you have time, please type this code. Then you will get understand why this code functions. And I think that's it for today's video. I already upload the code and the files into the GitHub repository. You can find the link down here. And also let me know if you have any questions, any comments, thoughts, and critics. So that's it. Bye bye.